Hey guys, these are your notes for section 9 for day 2. We're still looking at improper integrals, and this time we're not looking at area under a curve maybe to positive infinity or negative infinity. We're going to encounter some problems when the function that we're looking at blows up somewhere in our interval. So, I could show you by a picture. I think I'll just show you this way. All right, so let's say that you're looking at the area under this curve from here to here. There might be the case where one of your numbers is fine. It doesn't cause your function to blow up, but the other number isn't fine. Like this number might cause this function to blow up. So in this case, A wouldn't actually work. We want to leave it an open interval and then stop it here at B. So here's what we're going to do. We're going to identify the value that's the problem, and we're going to do, let's see, I guess the way it's written, I don't want to use the letter A or B, so I'll make up a new variable this time. So I'll call it, I don't know, P. Let's look at the limit as P approaches, hang on, I'll explain it in a minute. That's fine, that's fine, that's fine. Okay, so we want this to get super, super close to A, but not quite actually attain the value. Okay, but keep in mind, we're not doing a limit. We're not doing a limit from both sides of A, because this integral started at A, not including A, and increases to B. Increases. So what we want to do in our limit is we just want to like back up to A, not including the A. So how do I say that I'm approaching A but only from this side of it? Then I'm going to do as P approaches A from the upper side. Likewise, if your problem is here, then I'm going to go limit this one's fine. I'll pick a variable for up here, and I want P to approach B. However, we're starting at A, including, and we're coming up to B. So really I want to approach B from just underneath it. Just underneath it. Okay? And then lastly, sometimes you might encounter, these are kind of hard to see, these are a little bit tricky, where these numbers are fine. These numbers do not cause your function to blow up, but there happens to be a number in between them somewhere in the interval from A to B. There might be a number or more than one numbers that cause your function to blow up. We have to exclude those numbers from our integrals. So we have to start at A, lead up to that problem number, exclude it. Start over again, exclude it, and lead away from that number and head to B. So this is what it's going to look like. Okay, so I've already used P, so maybe I'll use P and Q. Okay. It's going to require some thought. A and B are fine. So from A, A and B are fine. So I'll go from, oh no, I only need one letter, to P, limit as, I get it. It picked the letter for me. C is the location where it blows up. So I kind of pick a random letter here, and I'm letting this approach this from the underneath side of it. And then same From the upper side, yes, because I want from the upper side of this leading up. This is leading up to the lower side. So, quick summary. More improper integrals don't involve infinity, but one or more of the numbers, either in your upper limit or your lower limit, or somewhere in your interval, causes your function to blow up. We need to do our integrals and exclude those numbers, but get as close to them as possible. All right. So in this first one on the back, you can see that I checked these two first, and 0 is fine, 3 is fine. So is there a number in this interval that causes this function to blow up? And yeah, you can see that it's 1. So my problem is going to happen when x is 1. Okay, so let's exclude 1 from our integral. Here's what that's going to look like. All right, so I said, let's go from 0, let's stop it at 1. So you can make up a letter, send that letter to 1 from the underneath side of it. Pick up where we left off. I guess I could have used B again, it doesn't really matter, but starting at 1, just from the upper side, and going to 3. Now, I really kind of in my head used u substitution to do this integral. So if u is equal to x minus 1, I've got 1 over u to the 2/3. That's really u to the negative 2/3. When I raise it and divide, there turns out to be a 3 out there. And that's like, yes, it's messy, but it's super simple messy because du would only just be 1. So it's a very quick and easy u substitution. Okay, so anyway, did my antiderivative, haven't subbed anything in yet. When I go to sub stuff in, I went ahead and wrote this as an root. Okay, wrote it as a root. Left the 3 on the outside, just I didn't want to fool with it. I could have just put 3 around the whole thing, I guess. So I subbed in B, subbed in 0, subbed in 1, or no, subbed in 3, subbed in A. And then, ready? As I approach 1 from the underneath side, so think about like 0.99. 0.99 minus 1 becomes a tiny negative. The closer you get to 1, the tinier this becomes. Okay? Oh, I did it. Yes, that has nothing to do with B. Whew, space there for a minute. Sub that in, get a value for that. Yes, and as A, subbed in A, as A approaches 1 from the upper side, so like 1.0001, this becomes a tiny positive. So, this is headed toward 0. This is headed toward negative 1 times a negative 1. Right? I end up getting 3 times positive 1 out of this set. And then that just is what it is. That's headed towards 0. So I got 3 times this. So 3 times a positive 1 plus 3 times the cube root of 2 looks like that. And I could say that that converges. Okay. Don't look at this graph. This graph is for later. But here we have infinite discontinuity and an endpoint. So check these two numbers. This one's fine. This one is where you have a problem. Got a problem here. No big deal. Replace it with a variable. Send your variable to 2, but remember we're going to 2 from the underneath side of it. So I did my antiderivative, subbed in b, subbed in 1. I'm losing it. Sub in b, b minus 2. Sub in 1. You get 1 minus 2. All right. And do your limit as b approaches 2 from underneath. So 2 from underneath, like 1.99. 1.99. This inside becomes a tiny negative. Absolute value it, you get a tiny positive. So natural log of a tiny positive. If you look at your log graph, that's way down, like at negative infinity. So this value is negative infinity. This is 0. So my answer is negative infinity, and we can say it diverges. All right. And then, this is a really good lead into what you're doing third 9 weeks. The convergence test. So, if we just want to know, like, okay, don't give me a value. Just tell me, does it converge? Like, could you get a value? Or does it diverge? Can we not get a value? Just answering those types of questions. What if you have 2 functions that are both positive? They're both greater than 0. So these y values are positive and these y values are positive. And what if this one is always the top one? What if these y values are always bigger than these y values? So I kind of drew a picture. And it's a very random picture. But I want my g values to be always bigger or equal to my f values. Okay, now I'm going to make 2 true statements. Let them sink in. Ready? If g of x converges, what that means is I could find the area beneath it, right? If g of x converges, that means it doesn't diverge. It doesn't grow and get out of hand. If g of x converges, then anything that's bound beneath it would also have to converge. If this one converges and this one is bound underneath it, then this one is going to converge. Likewise, if this one, the lower one, diverges, if it grows and grows and grows and grows and gets out of hand, then you know for a fact that the one that is bound above it is also going to diverge. So if the lower one diverges, then the higher one has to diverge also. Those are both true statements. What you can't say is if this one diverges, if the top one diverges, we don't know. We don't know anything about the bottom one. Right? So there are a couple of cases where we can prove some things, but it has to be set up right. We have to say, okay, this one is higher than this one, and this one converges. Therefore, this one converges. Or, this one is always higher than this one. Hey, I found out this one diverges. Therefore, this one must diverge. Okay, those are two true things that we can say. So, and I've written that out. I don't really care if you can write it out. All I care about is, can you implement it? And here's our question. Does this integral converge? Oh, I forgot to do part B. That's okay. I'll come back to part B. Okay, so here's what it's asking. Can you do this? And I'm thinking, use substitution, integration by parts. I got nothing. I cannot evaluate this integral without a calculator. And it already kind of gave me a clue that maybe you won't be able to. I cannot do that without a calculator. How can I find out something about it? Can I just find out, first of all, does it converge or diverge? So, here's what I need you to do. I need you to think really hard about a function that is very similar to this, that you can do an antiderivative on. Can you think of a function that looks super similar to this, where you're like, oh, yeah, I can do an antiderivative on that. I think a function exists, I think 1 over e to the x. It's the same as e to the negative x. You can do an antiderivative on that. So, oh golly, I kind of wish I hadn't written up. Let me erase this stuff. This was kind of me thinking earlier. So, this looks very similar to this, and we can do an antiderivative on this. Now, we can either compare these two now or we can compare them later. Let's just go ahead and compare them now. Remember, we're looking at x values only from 1 to infinity. So, when x is 1, this is e to the 1 squared, e to the 2 squared, e to the 3 squared, e to the 4 squared, versus e to the 1, e to the 2, e to the 3, e to the 4. So for each value of x, don't you agree that this is bigger or equal to than this one? Just the denominator. This denominator is going to be bigger than this denominator. What does that say about our overall function? If this denominator is bigger, then this fraction is bigger. If this is bigger, this is smaller. Smaller. How about this? This would be our top function. If I looked at it on a graph, the one I'm comparing it to would be the top function. So, I decided to ditch this integral and do this integral instead, because I can. I can do this. So I did. Remember, this is e to the negative x. So I did an antiderivative on it. E to the negative becomes negative e to the negative x. Sub in my numbers. Sub in a b. Sub in a 1. As b heads to infinity, this becomes huge. Negative 1 over huge heads to 0. My answer is 1 over e. What's that tell you about this one? It converges. And remember, that was the top one. The one that I just did the math on converged, and it was the top one. If the top function converges, the one that it's holding under converges as well. So my conclusion, you can see, is that. And then part B, totally forgot to do part B, but that's okay. Grab my handy dandy graphing calculator and go math 9. Oh, wait. If it converges, use a calculator. I don't know if I can do this. Yeah, at least not right. At least not just with 5 seconds of thought. I can't do part B. We're just gonna leave it at that. We did part A. We determined that it does converge. Okay.